So I'm a postdoc in Grappa, about to move well, I have two offers I'm pondering, but I'm currently until November at Grappa, University of Amsterdam. I'm talking today about the future of axion physics. So I have a brief overview of QCD AXION as dark matter candidate. Then I'll talk about what we're doing for axion radio astronomy, including axion miniclusters. And if there's time, I'll go through gravitational waves. So, well, the introductory slide on dark matter, just mentioning that we still need to understand a portion of content of our universe in terms of dark matter. Today, I'll focus about the possibility that light bosons in the essence of QCD axions, axion-like particle or fuzzy dark matter, can be the dark matter. So these are called weakly interacting scalar particles, or WISP. This is a slide that I like a lot. It basically summarizes what you need to know about these particles. So the Lagrangian for a scalar boson is here. WISP can arise as for example, as pseudoscalar particles are related, for example, to string theory model. I might get into this later. Here in this Lagrangian, V is a self-interacting potential that also includes a possible mass term. So if there is a mass term, then the dark matter WISP can be produced non-thermally, and its a coherent oscillation lead to an energy density which scales as the inverse Hubble volume 1 over r cubed, where r is the scale factor. This is what's needed for explaining the dark matter. One of the ingredients that are needed to explain the dark matter in the universe. You have a candidate that scales with this type of relation. We also have a vast phenomenology for these particles, so an interaction between scalar particle phi and the standard model that include interaction with photons or with a fermionic current or with other types of currents. In this case, I've used A as axion, since we have a pseudoscalar particle, but WISP are more generic and can include also boson and light vectors. So let's get into the axion. So the QCD axion has been originally postulated as a sort of, now we see it as an archetype of the WISP. Axion-like particles are particles that don't solve the strong CP problem, but are still behaving like the QCD axion in terms of spin structure and interaction with the matter and the photons. And more generically, we have these WISP that might also include bosons and vectors. So the QCD axion comes out of the fact that in the standard model you can have a term that reads like in this Lagrangian term here, in which G is the electromagnetic counterpart of the gluon field. The tilde stands for the dual, and AS is a strong force coupling. This Lagrangian is multiplied by a term, theta bar, that controls the matter-antimatter symmetry in QCD. So we expect, for example, a violation of C and CP from the strong sector, which is nevertheless not observed in nature. So we have a strong constraint on this parameter here, which can nevertheless take values of order 1. So this is the so-called strong CV problem. And the axion is one of the viable solutions. So the proposed by Roberto Pecce and Quinn was that to promote theta to be a dynamical field, and then it's the dynamics that settle the value of theta to 0, to a CP preserving value. Well, with along with a new field comes a new particle, the axion, that can be obtained once this field is quantized, which was independently obtained by Weinberg and Wilczek. In this case, we have our Lagrangian that gets modified so that the theta bar term is actually the axion field, which is a scalar field over the axion energy scale. So now axion gluon, this is a dimension 5 operator, and the axion energy scale acts as a sort of a renormalization, and it's directly related to the axion mass. So the axion mass is inversely proportional to F. The higher F, the smaller the axion mass. We now know that F has to be higher than around 10 to the 9 GeV for different astrophysical phenomena that would occur if FA were smaller. This pushes the value of M to be below around 10 millielectron volt. This relation is only valid for the QCD axion, as the proportionality constant here is lambda QCD square. While for axion-like particle, this lambda is a new term that sets the confinement scale in a new theory. So my review on axions has been recently accepted on Physics Report. It should be actually available this week. And from this review comes this figure in which I show on the y-axis the axion-photon coupling, which enters this Lagrangian term. As you see, F now is the electromagnetic field. So this G axion photon has unit of inverse energy, where on the x-axis we have the axion mass. Variable QCD axion models predict that the axion mass be proportional to G. So they lie on lines at 45 degrees in this plot, and are basically given by this yellow band here. We see that there are various experiments that in the future will or are already able to probe this yellow band at different mass ranges, which are all possible data points for the QCD axion to exist. If you step away from this yellow band, you go into the axion-like particle region, which has already been constrained by some experiments like CAST, or by the duration of the supernova 1987A burst. So the early universe dynamics of the axion, we have to embed the axion into a complex scalar field in order to make this new particle part of the standard model. Then we introduce a Pechequin field, which is this U1 field, of which the axion is the angular variable here. And we also have a new scalar rho that is the radial mode. We expect the new Pechequin symmetry to be broken when the temperature of the universe is of order Fa. In this case, your potential for the Pechequin fields develop a new true minimum in which the Pechequin field sits. And this sets the value of rho to be of order F, while the axion field is free to move in the bottom of this potential anywhere between -pi and pi. It is then at much later temperatures in the universe, but on top of this, you also have the non-trivial effects from QCD that tilt this Mexican hat potential and make the axion field oscillate about the true minimum of the theory. These oscillations store energy So the axion behave as a the axion field is a pendulum whose energy density redshift as one of the inverse volume. So it behaves as a dark matter component. This can be placed more rigorously by talking about the equation of motion, which includes the Hubble friction and the value of the axion field times the sign potential. So the axion also moves in a cosine-like, in a periodic potential, which is here approximated as a cosine. We see that for times before the oscillations are set, so when the Hubble rate, the Hubble friction is higher than the axion mass, then I can neglect the value, neglect the mass term, and then one solution to the equation corresponding to this is just that rho is constant and theta is constant, theta dot is 0. Then we have a dark energy-like behavior. When the axion field is then set in motion, because h falls below m, we recover our damped oscillation, and then the energy field behaves as a matter field. So this is the parameter space of the QCD axion, which has been covered in depth in the literature. We have on the y-axis F, so the axion energy scale, or equivalently the value of the axion mass. While on the x-axis, we have the energy scale of inflation HI, which for a single field low roll inflation is related to the tensor to scalar ratio. So I'm going to focus only on this part of the plot in the talk, which corresponds to the region in which we have inflation at a scale which is much higher than the scale at which the Peccei-Quinn symmetry breaks. So we have inflation, and then the Peccei-Quinn symmetry breaks. So in this scenario, we don't have inflation that helps us with the topological defects that come from the spontaneous symmetry breaking of U1 symmetry. The scenario has then to be explored with the aid of numerical simulations, which find that the value of the axion mass, so the value for which we have 100% dark matter axions, is of the order of 10 to 100 microelectron volt. And there are various recent paper that covers this in the literature. The idea is that when the temperature of the universe is over Fa, we have the Peccei-Quinn phase transition, and then due to the Kibble mechanism, we have a formation of a string network, which evolves, and as we see here. So for example, if we take this part here in this box, which is a 2D slice of a 3D simulation, we see that the value of the axion field that takes all possible colors between white, which is minus pi or pi, blue and red, which are intermediate value, and black, which is 0. Well, in this box, the axion field takes all of these values circling a dot. A dot in a 2D slice of a simulation is a line in a 3D box. So this is a cosmic string. This type of simulations follow the evolution of the string network, which is then dissipated when the axion field acquires a mass. So when the axion mass is of order the Hubble rate. It is also in these simulations that we see the appearance of compact objects. So we have, due to these inhomogeneities in the axion field, we can select regions in this simulation box in which the energy density, so delta rho over the average rho, has spikes that form what are called axion minicluster seeds. So these part of the universe behave as seeds that then enter the nonlinear regime at around the matter radiation equality. So actually I have here 2 comments related to the previous talks. So I tend to agree with Carlos Frank about what he said about axion dark matter. It should behave as, at least from the power spectrum analysis, as cold dark matter down to the scale of these axion miniclusters, which have a typical mass of the order of the axion mass at the QCD phase transition, of the axion energy density enclosed in a Hubble sphere at the QCD phase transition. This is of order 10 to the minus 11 solar masses. And correspondingly have a typical radius, which is of the order of the Sun to Earth distance. I also have a comment that, along with Javier Redondo, in this paper, we have studied axion dark matter and axion minicluster in matter-dominated cosmology that have been mentioned earlier by Katie Mack. So, embodied simulations are needed in order to follow the evolution of these axion miniclusters and their hierarchical structure formation. So out of these simulations, you can extract the halo mass function for these substructures. This is what we are interested now at GRAPPA. We want to check how many of these axion miniclusters have survived tidal stripping. Say that we are in a region at the radius, the distance r from the galactocentric, from the galactic center. Well, then how many axion miniclusters are we expected to probe in this region? Many of them would be stripped away by passing from nearby stars by the effect of tidal stripping. Passing star would deposit some amount of energy, which would strip a portion of axions out of this bound axion minicluster structure, or even disrupt it if the amount of energy deposited is comparable to the binding energy of the axion minicluster. This is what I've been studying with Thomas Edwards, who's now a postdoc in Stockholm, Bradley Kavanagh, who's now in Spain, and Christoph Weniger, who's my current supervisor in GRAPPA. So we have taken the initial halo mass function from M-body simulations of axion minicluster, and we have Monte Carlo, and we have basically simulated the tidal stripping of passing nearby stars in order to infer what the actual halo mass function of axion minicluster after the tidal disruption is taken into account looks like. And we've done this for different orbits, for different eccentricities, and for different orbits of the axion miniclusters in the halo. So what we find is that, well, here we have the survival probability of these axion miniclusters as a function of the semi-major axis of their orbit. We have included both eccentric in solid and circular in dash, and we have assumed both power law or NFW profiles for the individual minicluster. Since these axion minicluster masses after the hierarchical structure formation range from masses between 10 to the minus 16 and 10 to the minus 6 solar masses, we have taken into consideration both. We expect the lightest one to follow a power law-like profile, and the heaviest one to follow NFW-like profile. So we see that NFW profiles are in general more fluffy and are more easily stripped. This is why the survival probability for a given radius, for a given semi-major axis is generally smaller. Nevertheless, at the location of the solar system, so 8.3 kiloparsec away from the galactic center, even in the most pessimistic scenario, so axion minicluster have an NFW-like shape, and they follow eccentric orbits, we still find around 30% of them to have survived. So far, the only piece of literature that have studied this has basically performed a Taylor expansion around the solar system region. So a picture that takes into account this result was missing in the literature. This is the same result, just in a different perspective. So the initial, before the stripping profile is a NFW-like profile, which then gets cored because of due to the stripping. So one application is microlensing. What is the fraction of axion miniclusters to the total axion dark matter fraction? So if we assume that all of the dark matter is in axion, then FMC here parameterizes the fraction of the dark matter which is in bound structures. The authors of this paper have used informations from microlensing to infer that, well, this is the line that you have to follow for the QCD AXION, to infer that around less than 10% of these structures should be in axion miniclusters due to lensing. However, we expect that lensing techniques would be affected due to the fact that we have less axion miniclusters both in our Milky Way and in the target galaxy that the lensing survey looks at. But this is something we have not performed yet. Instead, we have what we are doing is axion radio astronomy. So this is active line of search and looks at the fact that you can convert axion miniclusters, axions or other light particles into radio waves in the magnetic field of neutron stars, due to the fact that you have a axion photon-photon coupling. So the idea is that you model the magnetosphere of a neutron star according to some model, for example, Goldrake-Julian, which basically relates the magnetic field profile to the charges of ions and electrons around the neutron star, the rotating neutron star. Then axion photon conversion is possible when the plasma frequency is of the order of the axion mass. So this is a thin shell or a thin region around the neutron star in which this conversion is possible. One technique that can be used is to look at the individual neutron star and see if infalling dark matter axion produces a signal, a radio signal. This has been already taken into account to place some bounds on the axion photon coupling. What we want to do is a bit different. We want to look at the scattered encounter of individual neutron stars in the Milky Way with individual mini-clusters. So our power is the number of events that make this possible. In fact, we find that most of these axion mini-cluster neutron star event would occur in a ring-like shape in the Milky Way, with fewer events in the halo. For example, for an axion minicluster, for an QCD axion of 25 microelectron volt, you expect to observe a frequency of the order of 6 gigahertz. So when you plot that into a peak flux versus encounter duration plot, in which the peak flux is the maximum radio signal that you observe because the neutron star is closest to the axion minicluster, so the density is the highest, versus the duration of the encounter, so how much time the neutron star spends into the much larger axion minicluster. Well, we find that if we didn't include the tidal stripping, most of this flux would be of the order of 100, 10 to 1,000 microyears.
5 minutes left.
But the tidal stripping removes the most fluffy and largest axion miniclusters, and then we're left with just still with a significant amount of relatively bright structures, but with a shorter duration. So all of this is still preliminary. Now, I want to mention about axion stars. Inside axion miniclusters, it's possible that the QCD axions nucleate and form a condensate by gravitational cooling, so they lose energy. This has been shown in various numerical simulations, so that this leads to the formation of a condensate. How should we look at this? Well, this is like a particle in a box. We have some region R, which is the extent of our axion star. This would basically tell us what the velocity of the particle would be because of the uncertainty principle. So now we have some kinetic energy in these particles. We know that we know what the total mass of our hypothetical object is. So we know the number of particles times the individual mass of the axion that makes it up, and then we can build the total energy of the object as a sum of the kinetic energy, the gravitational potential self energy, and the self coupling, so the energy due to the self coupling. We look for an equilibrium solution when the gradient of the energy is 0. So this is what I've done together with people in Stockholm. We have solved for the Schrödinger equation, looking for the solution that behaves as a soliton. So we have a concentration of axions in the center of the star, and then we look for a profile that smoothly joins 0 at infinity. Once we have that, the mass is defined as of the object is defined as the total mass enclosed by this relation, and the radius is the radius that contains 90% of the mass of the axion star. When you plot this, this is the work I've done with Katie Fries, Sebastian Baum, who's now in Stanford, Javier Redondo, Zaragoza, and Frank Wilczek. Once you plot the rescaled radius in units of 1/, the mass as a function of the axion star mass in these units f²/m, you find that your as density increases, which is the one parameter that controls everything, you transition from a region in which gravity dominates. So this blue line, for example, explores the equilibrium in the axion star between gravity, the self-gravity, and the kinetic term, until density becomes so large that the self-interaction starts to dominate over gravity. So this red band here signals the fact that the axion star is kept in equilibrium between self-gravity and kinetic energy. However, this region here is unstable. So if you blow up the star a bit, this quickly get back to its configuration in blue here. Well, and then we have explored what happens when the density becomes so large that you start to probe all of the cosine potential of the axion. So you cannot perform an expansion in a small field. But then, in this case, the axion field becomes relativistic. So you are not able anymore to keep, gravity is not able to keep relativistic axions inside a compact object. They just escape. So these are oscillons that dissipate in a finite amount of time. So the only viable object that we can look at is axion stars that are in these dilute configuration, so low density configuration. And basically, this type of object is what is observed for ultralight axions at a much lower scale in mass and a much higher scale in the radius. Okay, I'm done. I'll go to conclusions since time is up. Thanks for the attention.